Okay, let's do a super free response over a bunch of other topics. So this is kind of a hodgepodge of topics here. Okay, so we clearly have a table there of time and B prime. So that's a rate in our table there. So the volume of a spherical jumbo beach ball expands as air is being blown into it, and it maintains its spherical shape. The radius of the ball in feet is modeled by a twice differentiable function of b of time t, where t is measured in seconds, t is between 0 and 10. Graph of b is concave down. The table above gives selected values of the rate of change b prime of t over time from 0 to 10. The radius of the beach ball is 5 feet when t equals 1. So b of 1 is 5. That's a point on our original function. Part A, approximate b double prime of 9. So approximate the derivative at 9, and 9 falls between these two. And so we want the slope of the point, or the slope between those 2 points. So b double prime of 9 is approximately the slope between the 2 points of the function before that, the original function before b double prime, which is b prime. And so that is 0.7 minus 1.5 over 10 minus 8, which is negative 0.4 feet per second squared, because that 0.7 and that 1.5 on top are in feet per second, and then the 8 and the 10 are in seconds, so feet per second squared. And interpret this in the context of the problem. The rate at which the beach ball is being inflated is decreasing at a rate of 0.4 feet per second at t equals 9 seconds. So the rate at which the beach ball is being inflated is decreasing, because it's negative, at a rate of 0.4 feet per second squared at t equals 9 seconds. All right, part B, evaluate the integral from 0 to 10 of b double prime. So that table is b prime, not b double prime. So we're not doing a Riemann sum or anything. And so the integral from 0 to 10 of b double prime, we can use the fundamental theorem of calculus. This is b prime of 10 minus b prime of 0, which are just points on the graph, or points on the table, which is 0.7 minus 4.2, which is negative 3.5. And then explain this in the context of the problem. This says that the rate at which the beach ball is being inflated decreased by 3.5 feet per second from t equals 0 until t equals 10. So the rate at which the beach ball was being inflated decreased by 3.5 feet per second from t equals 0 to t equals 10 seconds. Part C, estimate the radius of the ball when t equals 1.5 using the tangent line approximation at t equals 1. So first we need the tangent line approximation. And so the slope at t equals 1 is on the table. The slope at t equals 1 is 3.2. The point at t equals 1 is the 0.15 that we were given in the paragraph up there. And so the tangent line is y minus 5 equals 3.2 times x minus 1. That's the equation of the tangent line, and then we're going to use that to estimate when t equals 1.5. So y minus 5 equals 3.2 times 1.5 minus 1, which is going to be y equals 6.6. And then, is your estimate greater or less than? Well, that depends if that function is increasing or decreasing, and we are told that b of t is concave down, and that means that b prime is decreasing, and so this is greater. This estimate is greater than the true value because b of t is concave down. And if you're unsure, you can always draw a quick sketch of that to see what the tangent line would do. So if we are concave down, then our tangent line, no matter where we put that, if we're estimating here, then the line is above it. And that's how that works. Okay, part D, use a right Riemann sum with 5 sub-intervals to estimate or approximate 0 to 10 b prime of t dt. So a right Riemann sum means we are not using the left side. So we're looking at the distance between the x's. That's 1, 2, 3, 2, and 2. And then times whatever the height of the rectangle will be, which is the y value. So that's going to be 1 times 3.2, 2 times 2.6, 3 times 2.1, 2 times 1.5, and 2 times 0.7, which you would, this says to not do with a calculator, which means this would be a little bit messy. And so you just go ahead and leave this written out so that you don't make an error, and that's okay to leave this like this. Now the answer is 19.1, but you can just leave that as the written out Riemann sum. All right, incorrect units. Explain the meaning of that. So the integral from 0 to 10 of b of t, that is the total amount of b, right? That's the accumulation of b, and b is the radius. So that means the ball's radius increased by 19 feet, 19.1 feet from t equals 0 to t equals 10 seconds. All right, is that an over or underestimate? Well, since b prime is decreasing, then our Riemann sum is an overestimate. So if you draw a decreasing function and we draw a right Riemann sum on there, so there's a decreasing function, there's a right Riemann sum, and so our approximation is an underestimate. So underestimate because b prime of t is decreasing. Part F, find the rate at which the volume is changing with respect to time at t equals 1. That is a related rate. So find the rate at which the volume of the ball is changing with respect to time. That says find dv dt when t equals 1. So we must need a formula for volume. I don't anticipate the AP test would make you know this. In fact, I'm almost positive of it. So they would give you some formula like that. And we take the derivative, dv dt is going to be 3 times 4/3. That's going to be 4 pi r squared dr dt. And we are looking for dv dt when the radius is 1. When the radius is, or sorry, when t is 1. And we saw from the beginning that when t is 1, the radius is 5. That's in our original paragraph. And when t is 1, dr dt, the slope is 3.2. That's in our table. So dv dt is 4 pi, the radius, which is 5 squared, times 3.2. 5 squared is 25, times 4 is 100. 100 times 3.2 is 320 pi. And that is dv dt, volume per time. That is cubic feet, or feet cubed per second. All right. Part G, is there a time t when b prime of t equals 2? So is there a time? That means you are looking for intermediate value theorem or mean value theorem. Okay? And so since we're dealing with all derivatives, we're not actually taking the derivative, we're just talking about the derivative function, this is intermediate value theorem. And so we need to look at the two ends here. And so b prime of 0 is 4.2, and b prime of 10 is 0.7. And so b prime of t equals 2 will fall somewhere in there. So if 2 is between 0.7 and 4.2, then t is between 0 and 10. So how do we put that into words? We can say that since 2 is between b prime of 10, which is on the low end, and b prime of 0, which is on the high end, the intermediate value theorem says there exists a time t between 0 and 10 such that b prime of t will be 2. And one more thing, we have to say that the function is continuous. In order for that to happen, we were told it's differentiable. So we somewhere have to say that since b prime of t is differentiable, b prime of t is continuous, because we can't use intermediate value theorem unless it is continuous. Okay, so we're going to leave that like that. That is a bunch of kind of random things, a lot of units, a lot of describing, writing in the context of the problem, to help with the other category.